Only study you have to study for demonstration, study station, suitable is to go for like around 3 sessions. Like, yeah. Appreciation of work, conversation. Yeah, we look at this down with the now. Yeah. 60 minutes of stuff. The first one, let's get this presentation done today because it's important. I have to do it. It's shiny. Reason why we are doing this is because of this. Yeah. Charity plays an important role an important role in the opportunity to this continuous polarization directions where the polarization is of cutting external conditions. For example, I have Branson. Keep playing the game. Playing. Okay, anymore. Consider 6 legs in a point load on his pieces of as symmetry determines the greatest continuation. Drop the straight down As an example, This plays an important role on a species group and the seems to determine the continuous polarization direction. Where the polarization makes use of certain external conditions such as temperature, chemical composition, pressure, electric field, etc. For example, the polarization can be developed then we can give it a higher pulse. On the heater, you can give a higher remnant polarization but low corrosive field. But for tetrahedral, you can get a very high corrosive field. Why do we need a high? What does high corrosive field mean? High corrosive, simplifying, square, big. Repetitions higher than the corrosive field of each other. And why the corrosive field of polarization is slightly lower than that. Yeah, put that on. courses. What to do with thickness? 233D. D3, D31, D33, D31. Oh, wow. Well, the course is filled for which one? Function technique. Terminal polarization course is filled as a function of thickness for 100 and 111 thickness. The field was 200 kilovolts per centimeter. The frequency was 30 Hz. So 100 shows a higher what? A coercive field, but lower aluminum chloride. Why does coercive? Why coercive field is important? Oh my! Wow! Another begin. Then this is all with the properties. I'm just trying to find something that I could understand I can put in my presentation. The investigator the mechanics properties of solid drive laser can attack and make control to the dialectric constant for 136 from 10-20% higher than that of increases with the previous technique. However, one of the statements about the piezoelectric coefficient D33 and D3 and with some techniques, such as the technique created by another autonomous emitter. As that coercive coercive field chemotherapy, coercive field, and including the dialectric constant. The property of pairs in the case of friction that requires to be used for the reason of the element. So, this is summary to give Begin terms, key terms, keywords, and frame. How can I represent my beam of presentation? I don't know, man. I don't think I'm gonna get it done, but I'll try my best. Where's the field keyword? Like, so it's keyword and both. Oh man, this is I can't do it. Thickness is just not like mine, so it's too high. I'll get to that. All the way from there. If you no? Really? Let me see, why doesn't all around? feels like its soul. And to this is everything. Visibility, underline towards parentheses, color to stands out. Thank you for 需要维持什么小金件？这外面，这是什么？嗯。Directly property is a property related in the case of education and education and education. Continues with the supervision. Word application is in education. Continues with the these properties relate to the material security, ability to store and release electrical energy, the property related to material verification and release electric properties, electric properties, electric properties are characteristic material continuous usually to probably concept like concept. I just wanna keep the electricity. and external electric field. I can know the words, the keywords, what does it mean by laminate variety? So that will be laminate, and then the residual polarization. That's the main material electric material of the thermal electric field. Residual process in the elimination of material creates material after the monotropic phase boundary accomplished. Has to be considering material to material where there is a change in crystal effect. That's most of the problem. Once you do understand the keywords, then you will be good to go. 9, 4, 12, 6, phase boundary in between. And BT and MTD. A compositional range differences in different realistic materials where there's a change in crystal structure leading to enhance. Microscopic phase boundary clarity. Where you make this a certain estimate of the something. What's in TV? There's a transition between different systems. There's a transition. Between different philosophies. There's a transition. Plastic. Property itu yang bukan sebagai physical yang jadi the computation boundary between plasma dan the user Let me see how does it look like now. I think it's a lot of light. So maybe now, I think it's good because I think now I can estimate myself. Yep. Shut down some stuff. Look at that. Making me throwing up. That's difficult, running until I read I'm trying to there's a bit bigger looking into properties. The component late opinion. Report reviews, copies of material development continuous liquid service and the individual application and external to the field. Piezoelectric properties. Resources and materials that have continuous liquid polarization and can be reversed by application and external to the field. I like and then this properties of the material. Sorry. This is this it's a lot. Continuous electric polarization. Physical properties typically they have a continuous electric polarization. Residual polarization. Extra polarization and becoming determined the figure between the chemical research and Where's that? What's it called? What is it? Jesus. Fragilistic line, fragilistic system, diluted material, material. Diluted material, I cannot take it into the game. Diluted fragile. Diluted material. Laser gun dedi. Şöyle yapıyoruz, şöyle patlıyor. Devam et, göstermek. property, residential, America material to be able to sell. Okay, element polarization. This is your precision dimension of electric. Element polarization, the residual polarization, the dimension of ferroelectric material for external transition between catastrophic data. Okay. Boom, boom, boom. The composition of boundary between the diagonal is of material. God. What else? Let's do the fraction, FRB. Let's do the fraction of the community economic atomic material surfaces of fragments serving at atoms within the crystal, fixed within the situation. More. Oh no. All the things can understand. Atomic and significant determine the atomic molecular structure. Structure of a crystal by scattering X-ray beams at the atom within the crystal. And then showing the atomic and molecular structure. Atomic and molecular structure. By covering the shooting object. It is need for elementalization of the topic based on the what is that? That one looks here that episode. Electric permittivity, no. For the course field with the specific property of ferrous material. And the density of electric permittivity is minerality in the case of chloride formation. Electric constant, electric property. Yeah, that is the constant in there. Drag your heart and everything right. electric field required to use it's the electric field needed to reach the polarization. The electric field needed. The polarization if the electric field needed to break the polarization of the direction of the also speak on it and to the original material to do operation especially by putting through the electric field required to reduce the polarization of the material to zero. Here's the program density of the opposing field. Offset has been calculated. Nothing's done. Inside's done. The individual electricity required to reduce polarization of the material to zero for electricity needed to break the polarization direction of the electric material. Visible intensity of the material or of electricity required to reduce the polarization. The polarization of the material. Polarization of the material. Zero operating cycles are equal. This is down. Good book. Oh. Visualization demonstrate live on the ticket. Where the response together with to visualize. I think I remember everything I did on the video. Continue. Continue polarization. Oh no. This explain what does it mean? Okay, no, that's it. Oh, oh, wow. Oh man. Look at it. Message. This is the other kind of person for today. This is I still have presentation, look at presentation. Oh, I have it. Okay. What I'm gonna do? How can I add? And it's how can I add? Let me add references first. Oh, I didn't even do it. Acknowledgement, get back. And frame, oxygen, frame, okay, and frame, yes, encoding here, not group, not group, and the dumb group, now it's not working. Oh yeah, let's put them up on. Let's go join. Boom, we join man's password.
Think did I get messed up? Because yeah, no one else had shown up. But yeah, I didn't know. Yeah, like I said, we can
Yeah.
keep this brief too, because I know let everyone enjoy their holidays and stuff. But yeah,
Yeah. Thank you so much, by the way.
yeah, no problem. Like I said, it's works in progress. I don't know. Yeah, I mean, like I said, I know. Yeah, Karen and stuff from CHTM. They said more. More come. January they'll be able to start all the. I don't. Again, they said it shouldn't be that difficult, since you're already here. But yeah. So, again, I don't know how long the paperwork and everything. But yeah, so just and like I said, if you find something in the meantime, just, let me know, and fine. Yeah.
Yeah.
But yeah. So well, I guess I'll get started. Like I said, and I don't. Yeah, I didn't send a reminder and anything, and also I know it's the holiday season, so thanks for showing up. Keep this kind of brief. Yeah, hopefully you don't hear any kids in the background. My end. I think my wife took them outside, so for now. But never know if they come in and scream and stuff. So apologize for that. So just a couple of things that I have from my end. Well, Raul's not here, but I just wanted to let you know. So Raul's paper finally got accepted. So that's his first paper, in our group. Well, I mean, he had a conference paper, but his first journal paper. But yeah, so that's good. It was a headache. I don't think I ever submit. It was at Applied Sciences or something like that. It's a open access one, but I got they gave me free waiver, so I was like, okay, I would try there. I don't think I'll ever submit to them again. The review process was, I don't know who they had. The one reviewer, the two they had 3 reviewers. 2 of them were great. Basically the first time after the first submission, it was just basically minor revisions, and you could tell they were energy harvesting people. The third reviewer, oh my gosh, I don't know what the heck his problem was, or him or her, sorry. But yeah, they didn't know anything, and they were critiquing everything, and so it was a big headache. I think we ended up going through like 7 different revisions or something, which is sort of unheard of. But anyways, it finally got some accepted, so that's good. And Zainal, I know, your sensor paper is under review. Yeah. Hopefully they send it to the same, the same reviewers. This time of year, by the way, I mean, like I've gotten just in the last couple of days, I think I've gotten like 7 or 8 papers to review or something like that. So it seems to be very common like this time of year, because it's like, okay, semester's over, so now here we send it to everyone, and so so I'm reviewing a bunch of papers, but I usually get things done. I don't know if other people will or not, so I don't know the timing of it, if it'd go quick or not. But hopefully it'd be relatively quick for your paper. Mina's not here, but I know I have 2 of Mina's papers too that are also have been submitted that are under review, so hopefully a lot of papers coming out from our group in the near future. Also I was hoping to enjoy the holiday season, but then I got an email, or a notification of a potential proposal that's from Department of Defense. So it's only it's a 2-part one. So the initial one is just like a 4 or 5 page proposal, but it's due January 5th. I'm like, oh, that's not much time. They don't give you much time to do these usually. But it could be good. It's a lot of money, so it could potentially be good. And in the area, again, sort of material development is probably what it'd be focused on more than devices. So that's what I'll be working on over the next 2 weeks, I guess. Other than that, that's all. I think that's everything as far as the lab and everything else. So I mean, I don't know if you guys don't have anything to share, that's fine. I know, it's just finals just ended and everything. And I know some of you are traveling and everything else, but I'll just go around, and like I said, it could be quick, but if you guys have stuff to show, great. So, I don't know. Zeno, I'll start, I guess, you.
So I'm still working on, magnetostrictive experiments, and I'm training Fazli. I'm teaching Fazli with photolithography and other stuff. Good. And also, he taught me something, Dr. Jason, I was struggling with peeling off samples, and by using DI water, it's very simple.
Yeah.
We were able to peel all the samples out. So I will try the same thing for my tensile samples.
Okay.
After photolithography, hopefully I will obtain them and do mechanical tests, add mechanical tests to our current paper. So,
Yeah, that'd be good. Yeah.
yeah. I also plan to create a MEMS, cantilever at the same time, in addition to these current papers. So I plan to start, using layout program to create a mask, and I believe we can easily do photolithography and then maybe reactive ion etching, and we can obtain like 1 millimeter cantilevers if possible. I also want to try this. It might be a good comparison. It might be a good comparison.
Yeah, no problem. Yeah, I know the hardest part was always like the composites doing the etching. Yeah, I know that was difficult to do, but yeah, if we can do it. But yeah, I mean, obviously the photo imageable ones are always easier if we can do that. But yeah, if not, we can do So no, sounds good. Let's see. So Ranjit, it's a good evening, or middle of the night, or whatever. Yeah.
Actually, I was reading one of the paper.
Oh, that's interesting.
Yeah, this paper was from the Los Alamos.
Okay.
So they fabricated the devices. Basically, they used the standing waves, and in their main practical was like to compare the experimental as well as the simulation results.
Yep.
And they used particularly this part, like they call this one as a pressure node, and this is the anti-pressure node where where there is a high amplitude. So they used basically the single amplitude wavelength, and the both side has like a zero pressure, and the middle center of the channel will has the highest amplitude. And basically they says that because the has from the figure, the schematic shows that the tiny particles are flowing straight forward, and the bigger particles are like attracted towards the side walls. This is mainly, they say from the paper, that the force is directly proportional to the volume of the particle. So the acoustic forces is directly proportional to the size dependent, and the bigger particles are experiencing larger forces there, so they are attracted towards the side walls of the side walls.
Okay, very good. That was very useful.
And they use basically they constructed the device basically using the SU master mold, then using the soft lithography, then they poured the PDMS into that master mold, and they created again they aligned or combined using the permanent bonding under the microscope between the PDMS and the SAW device.
Yeah. Another thing, so I know they use PDMS. I can't remember. I know you presented it, but so that the mechanical properties of the channel make a big difference. But I was trying to remember: is it softer better, or stiffer better? I can't remember. Or is it
softer is the better, because it can undergoes the deflection.
So then that leads into using your EcoFlex potentially to because you've been doing some stuff with the EcoFlex measuring the mechanical properties. EcoFlex we can make the same way, and I said that would have it's even a lot softer than PDMS, so that could
we can compare basically the both PDMS is the stiffer one, and the EcoFlex, how the separation can occur on that. And we can talk about the physics beyond the stiffness of the material.
Yep. But so, I'm trying to. So who do you remember who the main person is at Los Alamos? I know someone who's.
This was the paper.
Or when was it public? Because I know there's.
It's a 2014 paper.
Okay, is it? Well, I can look it up. But is it?
It's the Babetta.
It's not. Is Steve Graves on there?
No. This is This is the author, Babetta Elmero.
Okay, I just can't. Yeah. Okay.
So I think he's in the other part is from the Singapore, and the other part was from the Los Alamos, one of the authors.
Okay, because I know because so I mean I ask so Steve Graves. I mean he's our I don't know what his position is now, but I mean he's a professor in CBE, but he used to work at Los Alamos, and I know he
Hmm.
started this work at Los Alamos, like looking at surface acoustic waves. But I know I talked to him when I first came to UNM.
Hmm.
But he wasn't a piezoelectric person. He goes, we just buy the, like the surface acoustic wave. Like they didn't really know how to do it. But yeah, I think he came after,
Just
yeah, before
understand.
2014. So, but it's probably the group that continued on. But I know he started even a company. Uh, I don't know what his company does. I don't know if it's doing acoustofluidics or not. But yeah, but I know he
Hmm.
did some of the work. So I was just wondering if it was him or not. I mean, no, yeah,
Okay, yeah.
yeah,
So this is the simulation results, and this part is the zero where the amplitude is there. Like the basically they are validating the material simulation results and the experiments.
hmm,
And the blue color at the walls, it's like a 2D model.
yeah, yeah,
The pressure node where the amplitude is zero, and the
yeah.
center of the cavity or the center of the channel, it's like a higher 0.2 the megapascal.
Okay,
So they did the simulations. Then during the experiment, they in the microchannel they used like a random particle distributed, and they applied like a two,
mm,
24 decibel the power, and the has the time increased at like 2 seconds. The particle is separated. So they're finally saying that the acoustic radiation force attracts particles towards the side walls.
yeah,
So how they are validated basically the simulation results and the experiments. And they did not talk about the another one was the acoustic streaming. They did not talk about that
yeah,
because the other papers talk about the acoustic
yeah,
streaming as well. They are talked mainly about the acoustic radiation.
yeah, yeah. Oh, very interesting.
Then they use the synthetic particles. This is a fluorescent. Without applying the power, the both the particles of different size, the green color and the orange color,
Hmm.
they are in the same phase. When they apply the power, the green particles is at the center, and the other particle different size is diverted towards the other channels of the microchannel.
Yep.
Then again, they used like the practical cells, and they segregated the particles. Initially, they mixed with 53% and 46%, and when they applied the power, it's like a
Yeah.
95% accuracy on the both like PBM, MC, and the separated E coil.
Oh, very good. Yeah.
And yeah, I think like we can also present if we have the synthetic material, we can segregate the particles, and we can separate based on this chart.
Okay. Yep. Good.
Yeah, yeah. I,
And
I was able to read only one of the
no,
paper.
no, that's great. Great work. Yeah. No,
Yeah, I was
that
stuck
that
in
looks like
this.
a very good, yeah, very good paper. So no, it's very,
Yeah,
yeah,
this was very good paper. Like we have like we got the like how can we present our results in the papers basically
yeah,
on this method and the fluorescent for synthetic
yeah.
materials.
Yeah, I went through a lot of the forces and stuff because that's always what I was like. It's like okay, I see papers that show okay it works and stuff, but then to make it better, you got to understand the physics behind it. So that is very good. Yeah,
Yeah, I
yeah,
think another one we if we are able to use this one node and or the second node, we
Yeah.
can talk about more about the physics also.
yep,
Like
yep.
how the two wavelength or the half wavelength will affect the separation of the particles. It could be the better one, I think.
Yep, yep, definitely. Yep, yep.
But
Good.
I don't know how to like
Oh, yeah.
how we can say that this is a one wavelength or this is a two second wavelength in the practical. It's
Well, you can calculate what the. I mean, yeah, I know you can calculate what the wavelength is. I mean, from the IDT. I mean, that's easy to
yeah,
do. And then well, if we know the channel width, so we should be able to figure out okay if there's only going to be So they actually they probably want low frequency. I mean, yeah, unless the channel width is very small, but yeah, I don't know.
yeah,
Yeah. Yeah, but that's it. There's a lot of optimization. It's not just okay, here, put this in. Yeah,
Yeah, yeah,
and it
yeah.
works. Yeah, I mean, optimizing everything. Yeah, it's gonna be. Yeah, but no, it's
yeah.
good. Yeah,
If you are able to see this one, like we can talk about the physics, like yeah, the acoustic radiation effect on the particles,
yeah,
basically these
yeah,
these these things.
yeah. At low frequency, we should. I mean, like I said, we should. I mean, again, I got to look at what the frequency, but I know the laser interferometry system can measure. We should be able to find stuff up to I think 5 megahertz, maybe
Yeah.
I think that might be pushing. I can't remember if that's the limit. It's somewhere around there, anyways, for our system. But so if we had a wider, a channel or something that needs just one wavelength or something, we should be able to visualize it or something. But yeah, that looks good. And even like how they go to the next slide that you had, I think,
1 minute.
or the one with the experimental data. I know. Sorry, the next one. Yeah, that one.
Yeah.
Or, sorry, the one above this. Like
this one?
No, the one above the slide, the previous slide. Yeah, this one. Like the experiments. I mean, those images look. I mean, that's all. Yeah, I don't know how they quite imaged all those things. They probably put some dye in the cells and stuff, and just it's probably.
Yeah, I think they used the camera. I think the slow motion camera to capture these particles.
Yeah, I don't know if we can do that, but I mean that looks great. I mean, yeah, if you can't, but if you can, but yeah, no, that looks good. But and by the way, so the little seed funding, did not get funded.
It's fine,
yeah. But again, they encouraged me to apply the next time around. So I mean, that's just again the universal, internal one. I mean, I got some feedback, so I can when I submit it again, I can. And some of the feedback it makes sense. It's actually most of it is more for the people at Toronto, because most of again the people that were reviewing this were they're medical people, so they were interested in the biomarkers and stuff. Because I mentioned we have biomarkers to for the cancer to land on and stuff, and but they're like, well, how do you attach this? How do you do that? Something like that's not really my area, so I gotta next time around before I write it off, send it to them to see what they that's not the main part of the proposal, but yet it's what the reviewers were interested in, because they probably know that area a little bit more. Like when I talk about acoustic waves, they probably don't have a clue what I'm talking about. So
okay,
but anyways, keep trying. That's all we can do.
Yeah. So Professor, one more thing. So you were asking me like, am I able to use the console from here? Yeah, I can use that.
Good. Yeah, because I'll send you. So the reasoning is so Radiant Technologies, that project they're continuing on. We're not really part of it, but the continuation part basically is they're going to make devices for us. So and I had ideas of making other energy harvesting devices, and this fits kind of with Raul's kind of stuff too. But basically I just want to do some basic to get the dimensions. I like what I have a frequency in mind, but I might send you some dimensions, because you already have their layers. That's the thing is, I mean, in the end I want Raul to do this, but you already have just taking their same layer thicknesses, same everything, but just change the dimensions, because they said now we can make it bigger. Before it's only like what, a millimeter in length or something. So now I want to make it like normal MEMS energy harvesting, like some of my old ones that are maybe like 8 millimeters or something like that, like much bigger. But I don't care about the power. I don't want you to, you don't have to do any of that, but I just want to know what's the frequency. If we use all their thicknesses of their layers, their elastic modulus, everything, I just want an idea for, is it 500 hertz or is it 100 or what is it, and then if we put a mass on it, like what's, like I might have you vary the length of the mass or something like that, and just give me some values for like what, and then I'll sit down with Raul and we can, design and
sure.
But that's the reasoning is, so they're
doing
that, and also like I said, potential, future papers, like I said, added to our other ones on like the interdigitated and stuff like that, because just
okay, Professor.
But that was the main thing. With ASCII, if you had access, just because. And the reason it's, I know they need us to have the complete design by, I think, sometime in February. Then but once we have the design of this, then we have to they're making us do the masks. So we have to do the masks, and like I said, Raul will do that. But and I know Abdul, you're doing that as well for your stuff. But so it'd be a little complicated, because they're like building all these. You guys really haven't done too much on building masks, so but it'd be good. It's free devices, so that's on like, hey, the more stuff we can put on there, and we get a full 6-inch wafer, so we could probably fit like several hundred devices on there, so it allows us to do a lot of different comparisons and stuff. So I'm trying to think
Yeah.
of everything, and once I think of everything, then I'll let
Yeah, sure, sure.
I'll send it to you.
Yeah, that okay.
Yeah. Other than that, try to think if there's anything else for you that I. No, I think that was it. Yeah. So okay. Yeah. Thanks.
Yeah, thank you, bros.
If you want to go and go to bed.
No, fine. I can.
Okay.
Yeah, I can stay.
So yeah, so next on the list, so Abdul, yeah, I don't know if you have anything, or anything you want to talk about, or
Yeah, yesterday, last week, Dr. Fazli, he tasked me with reading a paper. I did like not so good of a job in it because I was struggling with the basics. So I made like a quick presentation with just getting used to the keywords and stuff, and then
yeah,
I
yeah,
will delve more into the paper next coming session. And I also continue working with our modeling.
yeah,
I was able to do a sweep analysis with different voltages, because 100 volts, I don't think 100 volt is like a good voltage actuation voltage for the device that I have.
okay,
uh, so I'm doing a much lower voltage.
okay,
I'm just checking for each one of the voltage what would give me like a it might it might downgrade
yeah,
uh, uh, like if it's like a really high voltage. So
yeah,
I want to find the sweet spot. So that's what I was
okay,
experimenting with the console, and I'm learning more about frequency response of mechanical systems, uh, and so let me show you my presentation.
okay, yeah, and 100 volts is probably, yeah, because I forgot that your PZT is going to be much thinner, so yeah, 100 volts is probably too high. Yeah, again, 100 volts is what we use on the thicker one, like the 500 micron or something like that. But yeah, so yeah,
And yeah, I when we talked, me, you, and Dr. Plyle, like about creating like a Gantt chart. I also
yeah,
did that, but
okay,
I haven't I haven't solidified. I will
no
send you
problem.
an update.
Yeah.
So this is the paper that I read. Is the thickness dependence of electromechanical properties of solder drive lead zirconate titanate thin films with 111 and 100 textures. Basically, they have two different substrates, platinum substrates. One is with a 111 crystalline structure, and one is 100 crystalline structure. And this is and it was done by
Yeah, yeah,
F2 Zhu and McKinstry. McKinstry is
yeah,
also
yeah,
their contributor.
yeah, yeah,
So for the introduction, I just went over the keywords just to get an understanding. Sol-Gel process is a precursor, like basically a chemical solution which acts as the precursor for integrated network or gel of either discrete particles or network polymers. We are not working with network polymers. I believe we are working with particles, but ours is already done, so we don't need to do the solid process. We already have the precursors done for us. And then our material that we are making is lead zirconate titanate PZT. I was confused as to what kind of material it is. It's a ceramics perovskite material, and it has both piezoelectric and ferroelectric properties. And it contains lead zirconium titanium, and we can tune it the composition. We can tune the composition by the ratio of zirconium over titanium. The electric properties, basically how material can store or release energy, electrical energy. And ferroelectric properties is the like spontaneous electric polarization. And piezoelectric properties is the ability of of materials to create an electrical charge once applied by mechanical stress. Remanent polarization is the residual polarization that remains in a ferroelectric material after the external field is removed. And morphotropic phase boundary is when there's a transition between different crystallographic phase. In our case, for the PZT, is the compositional boundary between the tetragonal and rhombohedral phases of the material.
Mhm.
And here I have two pictures of why we are dealing with PZT 5248. The reason we are dealing with that is because we want a because for rhombohedral we can get a very high
Remnants.
remanent polarization, but our coercive electric field would be much lower. So given that, we would need a higher voltage or electric field for us to switch the polarization. And tetrahedral, if we have just only tetrahedral crystalline structure, that would give us a high coercive electric field, but a lower remanent polarization. So it will be the remanent polarization. Let me go back to the remanent polarization remains in the is the polarization that remains in the so that means that I wonder how would you explain this, Dr. Jackson, because I'm confusing myself, like this diagram right here.
Yeah. Fazli, do you want to?
Uh-huh,
You're probably the expert.
Yeah.
Fuzzy is
Sorry
here?
to interrupt.
Okay.
Yeah, okay. Just go a little bit, go to the PZT. Your one question was regarding to the PZT. Just go up. Yeah. So actually, go up more. Yeah, the PZT. So you pull up one of the paper for Dr. McKinstry, and we already discussed about that. Like as I explained you before, that PZT, like perovskite. So the first one thing, like we need to understand about the perovskite materials, that this have some distinctive arrangement, like in the formula of ABX3. So like in here in the PZT, can you open that paper, please, the McKinstry?
Mm-hmm.
Yeah. Because then I will come towards your question, the next one. Okay, if you see here Sol-Gel derived PbZrTiO3, like here, and you can see 0.52 and 0.48 O3. So yesterday, me and Zinel were also discussing about that. So actually, if you see this Pb in the bracket, you see the ZrTiO3. So this Pb is actually A site cation. This ZrTiO3 combinedly we call it B cation, which is located in the center of the structure. And this O is actually anion, which is surrounded by the central B cations in the octahedral arrangement. I will explain that you later on in the lab, that what this means, because we need to understand this thing before like to discussing more in the details. So we call such like structure perovskite material PZT. Now just go to the abstract, please. Abstract. Here is the abstract. Yeah, if you see here PbZr 0.52, Ti 0.48. Why this? This is very important. 0.52 and 0.42. 48. As I explained you before, this we call is the MPB, morphotropic phase boundary.
Mm-hmm.
Now go back to your slides, please.
Okay, where was it?
Slide. Yeah. Go to the phase diagram.
Okay.
Yes. Okay. So if you see here in the phase diagram, on one end we have the lead zirconium oxide, on another one end we have lead titanium oxide. Okay. So the mole percent is changing here. So if this lead zirconium oxide the structure of this one is actually rhombohedral. The lead titanium oxide structure is tetragonal. Okay, so when we increase this lead titanium oxide into lead zirconium oxide, so the point comes here at the close to 50, 52, that at 0.52 means 52 mole percent of lead zirconium oxide and for 48% of lead titanium oxide. This combines, there will be some coexistence of two phases. One is rhombohedral, one is tetragonal. So compositionally, when there existence of two phases and specific compositional range, we call it morphotrophic phase boundary. Now, again, your question was, if the temperature is changing and the structure comes with the temperature, I will explain you later about that. We call it PPB, polymorphic phase transition, or PPT, or polymorphic phase boundary. So polymorphic phase boundary comes because of the temperature variation, and morphotrophic phase boundary comes because of the compositional variation. So that's why they choose this, the morphotrophic phase boundary, because there is existence of two phases, rhombohedral and tetragonal. Why? Because rhombohedral, if we discuss more physics behind it, so the rhombohedral have specific orientation. We call it, they have 8 polarization orientation, and tetragonal have 6 polarization orientation. When they combine together, it will comes like 14 polarization orientation. So once you apply field on such material, so on a very low field, you will get a high maximum polarization in your material. So now comes here to your polarization electric field loop. So if you see here on the y-axis, we have polarization, on the x-axis, we have the electric field. If you remember in my presentation, when I just joined UNM that time, I presented some work to you that what mean by this thing, like electric field and polarization. So I explained step by step from the dipole moment, then domain walls, then grain boundary, and then I reached towards the spontaneous polarization. No, this is not remnant. Sorry, this is not remnant. So electric field will be, this will be, we call it the remnant polarization and spontaneous polarization. These two things are very, very different from each other. So actually, this point, when electric field is 0 and we get some polarization response, that point we call it remnant polarization. And also that material we call ferroelectric material. At the absence of electric field, if we have some polarization, the material we call is the remnant, the ferroelectric material. So if you see this, the black one, rhombohedral one, you see this rhombohedral one?
Yes.
This is huge. So this response comes because of lead zirconium oxide. And if you see this blue one, this response comes because of tetragonal. It means this response comes from the lead titanium oxide. But if you see in the middle, why in the middle? This is very, very important for us, because it have both response. Its remnant polarization and maximum polarization is decreased, but at the same time, it will give you both piezoelectric constants. Like you can use this for the sensors, and you can also use for the actuators, like to convert the electrical to mechanical and mechanical to the electrical. But the rhombohedral one, you can only use that one for most of the time because its remnant polarization is very high. So according to thermodynamic theory, you can only use for the sensors. But this MPB give you both response, and this is more dominant one. Like if you apply field more on that one, there will be no changing happens, and it will be much stable compared to the rhombohedral and tetragonal. Now again, you will see tetragonal have like a very high hysteresis loop. It means it shows you high leakage current because of corrosive electric field. If you see here, one corrosive electric field here is near to 30. Another one corrosive electric field is of red one is close to 15, and another one is close to 10. So this is very important for the conductivity response. So that's why many materials, like because of the structure variation, it give you different corrosive electric field, remnant polarization, and maximum polarization.
So why don't we use the rhombohedral? Because it has a high remnant polarization, meaning
Yes,
it can.
yes. This is a good question because rhombohedral we can use for specific applications. As I told you, if you study about the piezoelectrics, so piezoelectrics definition is to convert mechanical energy to the electrical and convert back electrical to the mechanical. So when it convert mechanical to the electrical, we call it static piezoelectric coefficient, the machine which we have available in our lab. Another one thing, when it convert electrical to the mechanical, it give you dynamic piezoelectric response. In other words, we call it indirect piezoelectric response, converse piezoelectric response, inverse piezoelectric response, which used for the actuators. So the MPB is good for both, and it is more stable because it will be more stable comparatively to the rhombohedral
Okay.
for the both applications. So you can use the same material for different types of applications. But rhombohedral you can use for the specific applications.
So the reason we are using MPB is because it's just
Yes, more
it
stable,
it's more
and
stable.
you can use for many applications.
Many applications.
Yeah, it's the most common PZT too. I mean, it's the
Yeah.
one that the company that gave us the salt. So basically, yeah.
Mhm.
But yes, it's good to understand. Like, yeah, no, that's good explanation. Thanks.
Thank you. And then
We
yeah.
will discuss maybe when we meet Abdul Qayyum. I will because the next task we will discuss about the crystal structure
Yeah.
is very important for you
Yeah.
because we need to understand the crystal structure. If I explain you what is rhombohedral, what is tetragonal, what is cubic, it will confuse you more.
Mm-hmm.
So we need to step by step. We need to start from the crystal structure just to understand
Yeah.
why these orientations come and why I'm choosing this structure.
Mm-hmm.
Yeah.
Yep.
But the definition says that is a transition between different crystallographic phases.
Yes. This means
Yes.
the coexistence of two phases.
Does it mean that one side is just like one kind of structure, the other side is different kind of structure? Is it like
No. When you do its XRD, it will give you both structures at the
what?
same time.
Okay.
There is specific peaks. I will show you in some of my papers later on.
Okay.
Yeah.
And then the last keywords that I learned was XRD. We use it's a technique that determines the atomic and molecular structure of a crystal by scattering X-ray beams at the atoms within the crystals. We use it with our experiments too. Dr. Fazli knows more about it. And then coercive field, the intensity of the electric. So I have a question about this one because they're saying the intensity of the electric field required to reduce the polarization of the material to zero after it has been saturated by an opposing field. Saturated means that they reached a level
Yes.
of
This is
polarization.
yeah, if you see the peaks, like the maximum polarization, it looks like a very sharp. So if you apply more field on it, your sample will be break down. So this is actually show you the breakdown voltage to apply on your material.
So coercive field is important for that, just to find the
Very,
breakdown
very
fault.
important.
Okay.
Very, very important. We need to control that electric field because if we can control this electric field and our electric field is very high, so we will lose a lot of amount of energy. Number first. Number second one, our sample will be break down and we can't use that sample for the device applications.
Okay, thank you.
This is very important to control. Yeah.
And then the last one, the electric constant, is the measure of how easily a material can become polarized by an external electric field. It indicates
Yes.
how much more electrical energy can be stored in a material compared to a vacuum. So
Yes.
we need how can we calculate our dielectric constant for our PZT? Is it like
So for this one, we will use the impedance analyzer. We have one setup. I think Dr. Jackson showed me that one. So that is the room temperature is a function of frequency. So I will send you some notes. We can understand that more in the theoretically way. but we will use the impedance analyzer to measure the dielectric properties as a function of temperature and as a function of the frequency.
As a function.
Because for the frequency, for the temperature variation, we need to find out its QD temperature. This is very important for us. I will teach you about that what is QD temperature, what is the depolarization temperature, what is the maximum temperature. And for the frequency dependency, we need to find out what type of defects we have. It's ionic defects, it's the electronic defects, it's the interface defects, or it's the something like a dipole defects. So we need to understand that more in the detail from the frequency variations.
And then
Yes.
here's the paper summary that I have. Basically, what they investigated was the electrical mechanical properties of solder-derived lead zirconate titanate of 5248 composition. We discussed why they use 5248 because of the
Yes.
morphotropic phase boundary,
Phase boundary.
and for 111 and 100 textures, the way that they got the 111 highly 111 and highly 100 textures was that they used platinums with the same crystalline structure as the substrate, and that's where they deposited the precursors. And the dielectric constant for 100 texture film was 10% to 20% higher. That's the result that they got than that of 111 oriented films, and in both cases the dielectric constant increases with increasing film thicknesses. So this was the main point that I kind of got from so the electric how fast how easy material can become polarized by the external electric field was higher for 100 textured films compared to 111 oriented films, crystal
Yeah.
oriented films.
So yeah, that's something like okay, I'll teach you about that later on, but this is like orientation of the films and specific orientation they are making 111.
Yeah.
So yeah, it will give you different response, and that response give you a different applications again. So I will teach you about that, like why they are guessing. But the most important one in this paper, what we were looking for, this is the material synthesis,
Yeah,
because we need to repeat their results. That what happens when we apply their way how they are making their films, because we need to compare that with the Mitsubishi project, and we need to find out the reason why this materials give us this response and which one is the more easiest one, because we need to find out some easy processing way to complete our project. Okay.
and then the other thing that kind of got my eye was that they talk about strong clamping effects. I wonder if the same thing happened with our results, like when we got like no 100 plane. Was it? Do you think it was because of this, like thermal mismatch between the PT bottom electrode and PZT film, or?
Yeah, it depends
Yeah.
upon the electrodes what you are using. So some people using like a BT bottom electrode, some people use the silver electrode, so different types. So it comes because of the thermal mismatch. So actually, most of the people use the PT bottom electrode because the thermal mismatch is more less than the another electrodes. So yeah, it's related to the temperature mismatch.
Is there like the thermal constant, thermal expansion constant for PZT gonna be changing, like when we are heating it?
Yes, definitely,
Yeah.
maybe, but like we don't have any concern with that. We need to
Oh,
find out that from the QD temperature.
okay.
Yeah. But I mean, yeah, and it's no. I mean, like I said, everyone uses. I mean, the temperatures and stuff that we're using are. I mean, yeah, like I said, fairly common with other people are using. So I mean, I don't think it would, yeah, create too much stress, anyways. But, yeah. But it could. Yeah.
Yeah, and they said that but the other way, so one of them, the 100 showed a higher dielectric constant, but the downside was for 100 films there was lower remnant polarization.
Yes.
compared to the 111 oriented films. But now we're going to the methods. So this is how they started with the solid solution preparation. They started like from zero. They didn't have any solid solution prepared for them, and they used methoxyethanol process. I wonder why they use methoxyethanol. Is it like just like a reactant, or
It is the only they use for the catalytic media
Yeah.
just to solve that materials.
dissolve the material?
Yeah,
Yeah.
because just to understand sol and gel, this is very important word.
Mm-hmm.
So that's why sol and gel, how they comes this word. So that's why they're using some liquid media for the diffusion of two materials.
And they use lead acetate trihydrate lead
Yes.
as like the starting material. They dissolve that in the 2 methoxyethanol, and then I didn't understand what they mean by distilling the H12
Okay.
hydration.
Okay, this is very different method. I used with that. This is called we got Solgel method. So up to roundabout up to uh, processing number 5 and 6.
Yeah.
We don't need to do this. We need to skip because we already have the
Okay,
material.
okay,
So
okay.
we don't need to do anything.
Skip
So
this.
we need to start directly from the
5.
to crystalline deposit films, number 8. Yeah. So we don't need to do, so we need to understand how they crystallize the deposit film, what condition they use. So they use the 3000 RPM for 30 seconds,
Mm-hmm.
and then they pyrolyze their material on 340
For
only.
60
So, but
seconds.
we can, yes, and then they use the RTA for 30 second or 700. So this is something like we need to do by ourselves because up to 6, we don't need to take that to repeat this processing. This is actually they are making nanoparticles by
Oh,
using the processing way, but we already have, so we don't need to do that. Okay,
so
this is
okay.
more easy now for us. Thanks to Dr. Jackson. It's very hard process, by the way.
Oh, I know.
Uh,
That's why. Yeah, I
yes,
know. I
very, very
made.
hard process.
Yeah, I
Uh,
made some a while back, and it's very dangerous process
Oh
too.
my
It's
god.
very
So
dangerous
yeah,
process. So I work in that, and trust me, Abdul Qayyum, you can get like a good amount. This is a very high repeated process because a little bit continuation happen, your material is done.
yeah,
So I make some barium titanate nanoparticles, and that is very good ZnSNO3 nanoparticle. But this is challenging, but a little bit toxic, so it is very dangerous to handle this material.
yeah.
So that's why we don't need to do that thing. So we need to directly grow from the 6 lumbar stiff just to go to the spin coater.
Yep.
Yeah. That was it then. So and then yeah. Thank you, Dr.
Oh,
Fazli,
yeah.
for your
Thank you.
help. Yeah, that's it.
Yeah.
No problem.
Yeah.
So yeah, it's
And
good one. It's the good one. Yeah. The presentation, like time to time, we will discuss one paper in
mhm.
your work just for the understanding.
And also, Dr. Jackson, I find this
Yep.
paper, this is a really cool paper because
Oh, okay.
they use the different electrode design, and they go through like exactly how they manufactured it, and
Okay.
they're using and that's I think Friday we had no, the 2 days ago we had a discussion as to what do we use, like PT on titanium
Yep.
oxide or PT on silicon oxide. They use titanium on silicon oxide and they deposit PT on top
Yeah, yeah.
as the bottom electrode, and then they have three different designs. One is like whole. It's like
Yeah.
a ratio of like the whole membrane,
Hmm.
so it's not. It doesn't cover the whole membrane. Uh, and I'm reading their paper, and they're concerned about like the thickness and the width of the membrane, because those are the only two parameters that affect the performance of the PMAT.
Yeah.
And there was another paper, and they also talk about like I will use this in my thesis. Actually, this
Yep.
is a really good way of modeling the device. You have electrical domain, mechanical, and acoustical domain, and what they were saying that the media can also impose a resistance over the device. So
Yep.
we like, for example, for water or for a viscous fluid, it would function differently, and it would it would need more power, or and
Yep.
the way that they define they use this equation to define the power usage of the device. So it's pretty cool. And
Yep.
also they talk about how they characterize their PZT layer, and they also talk about residual stress uh, between the layers and the thickness, how it affects it. So these are the graphs that basically talks about it.
Yep.
At lower thicknesses, it will have a higher. At lower thickness, you will have a high residual stress,
Yeah.
which would make your frequencies to be like not exact, to have a higher chance of deviating from like uh, like if it was 200 like megahertz, like if it was 2 megahertz, it might go up to 3 megahertz or
Yeah.
down because of the residual stress. Yeah, I will send you this paper. It's if you wanna go over it.
Yeah, sure.
Yeah, and there
Yeah.
is a.
Go up to the go. I mean, if you're done, just go up to the top. I just want to see who the author. Yeah.
Do you know these guys?
It's go down. Sorry, I was just looking at the. Okay, there. Oh yeah, I know Piers. Yeah, yeah.
You know? Okay.
Yeah, the final guy. I mean, the other people I don't. The students and stuff I don't know. But yeah, yeah.
And then also there's
Piers, yeah.
another paper that's kind of that might be applicable in our for VMAs. This paper, which I also thought was pretty interesting. So they are making holes on the corner of this rectangular membrane.
Yeah.
And that way they are making it more planar, which helps with transducer for transmitting transmitting frequency signals. But in our case, I wonder, like for vibrating mesh atomizers, if we were to do the same thing, because that way the holes also work as a fluid deposition, and then we have a different size hole in the middle.
Yeah.
Or is it like yeah, my question would be like, the mode that they are looking at is kind of like planar. It's not mode 01 or mode 02. It's like a piston, like, yeah, it's like a planar kind of mode. I wonder if that would help, like with the
in our case, yeah. I don't know. Yeah, I'd have to send me the paper and I'll look at it and see. Yeah. This one, okay. I don't know those, those people. Yeah. But send it to me and I'll look at it and see. Yeah, it's possible. Like send that, yeah.
Okay.
Okay, yeah, no, thanks. So, thank you. Jaren, I don't know if you have anything you wanna.
Yeah, Professor. I just started from today, so that I can complete something next week.
Okay. Yeah. So I mean, you're still working on the finite element modeling, basically, of that.
Yes.
So yeah. So I sent you a paper. I mean, I know. I mean, again, look at it. Yeah, it was like, they were using. Yeah, I think I probably read that one before, but I know I sent it to, Dr. Mattel as well, but he said he's familiar with that one. That's the method that they use. So, but again, there was just someone using paraffin instead of the EcoFlexes. But it was interesting, the test setup and stuff. Again, it's good to keep reading and to look at these papers because, like I said, eventually, I mean, right now you're focused on the modeling, but then eventually, again, we're going to do some experimental. So it's good, if you can find out how they set up the experimental testing and and what they use for the artificial skins and all this stuff, again, just helps you. It helps you in the long run. So then, once we get to that section, then it'll go a lot smoother. So keep up with the reading and the modeling. I mean, like I said, in that paper that I sent, you don't have to worry about the electrical stuff and all that kind of stuff that they were talking about, because they were using I can't remember if that's the paper. No, wait, sorry, I sent you a different paper. Sorry, I sent you a couple papers. The other one I sent like a month ago or so. Yeah, they were using the like they were putting metal electrodes. They were using it for bio, but it was still. But they were looking at the insertion force. And actually, I will send you probably an updated paper on that. That they. I'm just trying to figure out how to best send it because it hasn't been published quite yet. I'm reviewing it, so I'm not supposed to be able to send it to you. So, but yeah, I'll work on hopefully it'll be accepted soon, and then I can send it to you. But they went through a bunch of different designs for barbed needles. That paper they looked at 4 different ones, but again. That's why I said, those are 4 possible ones that we could look at when we get to that point. But yeah, I'm always happy to look at more. The more, the better. It's like, again, because it's like, okay, but I know, but you don't want to just look at thousands of different ones because that would take way too much time. So yeah, we just got to figure out like what's the best ones that we can fabricate and look at, and then go from there.
Sure. Thank you, bros.
Yep. No, thanks. Fazli, I know we're out of time, but I don't know if you have anything quick to
quickly a few things, and because I'm writing a report on that.
Yeah.
Can you see my screen?
Yes. If it's a Word document, then yes.
Yes. Yeah. Word document. Okay. So I will just briefly go, but I'm writing some report on that. To write some more stuffs with that. Actually, the XRD machine was down last week. There was some issue in that. They want to fix it because there are some people working for the temperature.
Yes.
So there will be the first one work, what we will do. And that will be the inducing of the barium titanate nanoparticles in the polymer polyvinyl difluorides composite for the electromechanical response, like for the piezoelectric, for the dielectric, for the ferroelectric, to check the resistivity of the material. So all the readings we will check for the based on this one composite. But actually I start from, because before we don't have the DMF solution, and we have one which was expired. Yeah. But I also tried that one, and I use like the way, and I put in the oven, and but it gave me this response, but I couldn't found here the aluminum peaks.
Yeah.
But then when we get the new one, I tried again, and I just put on overnight just to see without using any annealing, and the response was, this is the like symbol, like and this I just zoom it more. So this is aluminum, this is the beta phase, and here there is something alpha phase also we have, but these peaks are aluminum, silica, and aluminum peaks we have, which I found from some papers. These are the reference. But then I try again another one which I used before in South Korea, 4-methyl 2-pentanone, and the response was this one. I will send you this Word file. I need to write my view, and I need your suggestion that what is the like a neat suggestion I will write about here. That ongoing plan mine is to include the barium titanate nanoparticles with a specific volume % solution, and which one, this one or the new one or the expired one. So I need to check more in details and to put my view on that, and I need to take your suggestion that which one will be the best one for us, just to start the barium titanate nanoparticles and that solution, because solution is very important for us. Because the barium titanate is ceramics nanoparticles, so this is very important to diffuse in the PVDF TRFE material. So this is our first manuscript about it, and I'm trying my best just to complete this in this coming 1 to 2 months. And because then the next plan is another one inducing another nanoparticle to see what's going on with some another nanoparticles. We will see also that one. And I have planned another one. I'm writing a report on that one, just the project, like a small one on that one. I also thank you to Zinal for a good discussion. But I need to study about the magnetostrictive and conductive response of the polyimide, like HD4110 composite nanofilms, by inducing the cobalt iron oxide nanoparticles. This material have high magneto response and this will be the nice one that we can see the response in our photolithography. I have also another one suggestions, like just to put in like some like a single element particles
Yep.
to see also. But this one I found in some papers, and we can try just to check its response
Yeah.
in the HD4110, and then we can make some devices for the magnetostrictive and conductive response. This is my, so I will do also this one. Zenal and me will do also this one
Me too,
experiment
yeah.
just to complete that.
Yep.
Because we also have one experiment on HD4110, which we are adding the terphenol D. And this is also another one manuscript. We can start with that one just to complete that experiment.
Yeah.
Yeah,
The,
but
the, the
I'm
co-
writing some report.
okay.
Just I'm taking some time on that
Yeah,
because
no problem.
I don't want to start something. I need to see some papers,
Yep.
and I need to my report, and I will send you just for your suggestion, and just send me your suggestion. So maybe
Yep.
we also trying just to go sometime maybe in the, because I discussed with Jonathan. So if I manage time with the Zenal, so maybe we'll do the magnetostrictive measurements of his materials.
Yep,
Yeah.
no problem. Yeah. So the cobalt iron oxide. So do we need to order that, or is that? I mean, yeah.
Yes, I will send
Okay.
you. Yeah, I will
Okay.
send you the because I'm making the
No,
Excel
no
sheet
problem.
for
Yep.
it. I
Yep.
need some more materials also. It
Okay.
depends upon you, like what you need to order. So,
Yep.
but I will send you some for the future also.
Okay. Good.
Because, but still, I'm checking about that because I don't want to waste money.
Yep. Yep. No problem.
So
No, thanks.
that's the thing. Like I'm looking for that more concisely about that one.
Yep.
So,
No.
but I'm just writing something like a report on that, and then I will send you my like view about these two papers, and
Yep.
I need to take your suggestions
Great.
about that. Yeah.
Nope. Sounds great.
Another one thing. This was a huge training of the clean room. I already did, and I'm allowed now to use the send facility. So I will
Yep.
send you one email about that because we just reserved timing for more of the SCM tool. But if you have something more to learn about it in the Ascent Lab, because
Yep.
they told me you need a physical training for different machines.
Yes.
So please
Yeah.
let me know, like, because I need to make a reservation for that because
Yep.
then it take more time from me. Like, for example, they don't have much reservation. So
Yep. Yep.
it's very important. Yeah.
Yep. Nope. Sounds good. Sounds great. Yep. Okay. So yeah, I think that's. Oh, sorry.
Dr.
Go ahead. Yep.
Jackson, can you
Yep.
give me 3 minutes in-person meeting,
Yeah.
please? Now, just 3 minutes.
No, well, I'm not. So after I can do it after this, but I'm not there, so I'm at home, so I can't do it in person. But sorry.
No. In the
but-
online.
Oh yeah, online. Yeah. We can let everyone go, and then yeah, no problem.
Okay.
Okay, so
Thank you.
yeah, so everyone, yeah, thanks for coming. Like I said, and yeah, I'll see everyone. I'll see about next week if we're gonna have a meeting or not. But yeah, because I know it's during the holiday season. But yeah, thanks, and yeah, I said if anyone has any, again, good results to show, again, please feel free to send them to me. You don't have to wait till the meeting. But everyone have a good, holiday, and I will see everyone next week. Yep.
Thank you, Bruce.
Thanks. Yep.
Thank you, bro. Thank you.
Okay, I'm gonna get out. Fast. Oh man, I'm tired, man. Session 2. Yeah, I don't think I cared my fasting, and that's it. I have to. Bro, it's so much results. I didn't do that much of file save as insights for my next Q1. I think it's Q1 2024. I don't know. And How much, man? What do you want me to do? Q1 is quantified. I don't have anything. Shit, man. Besides, OKRs. I did whatever I could. I did whatever I could. Honestly, I don't give a damn. I don't think I have an idea of this clock. You're gonna I'm just tired, man. Anything else? Been busy. I've been. Hey Murphy. Oh, okay. Making more professional, bro. Technical challenges to get out of me. Yeah, I just. Finalize this, send this to as my thing is done. Holy cow. 5 minutes. remanent polarization. Yeah, whatever. Polar. Okay. Oh man, it's cool and everything. Even doing this is kind of like insane. Oh man, I'm just gonna read. For the next 5 minutes, I'm just gonna read. I'll just. It's 3 hours. I wanna go to measure and take a break. Oh yeah, listen this one. It's me all this. PCT. The links. Oh no. Is it? Yeah, yeah, I'm gonna be that. Oh, and then piston lag membrane mode. I'm done.